Hello, chemistry students. Professor Sean McMahon here. And in this lecture series, we'll be covering Chapter 11, Acids and Bases, and the chemistry behind them. So let's first do some basic definitions of acids so we're familiar with what they are and some of their characteristics. So they taste sour. So if you think of lemons have citric acid. So do other citrus fruits. But one of the things we notice about the acid, it tastes sour. Acids can dissolve metals, and we'll see in our later lecture 2, we'll review some of the basic reactions like the single displacement reactions where we add things like zinc and magnesium to metal or to acids, and they would dissolve producing hydrogen gas. They turn litmus paper red. Okay, so litmus paper is a way to test whether or not something is acidic or basic, and if it's acidic, it will turn it red. Some of the common acids include hydrochloric, sulfuric, nitric, acetic, carbonic, and hydrofluoric. We'll also review a lot of naming. We've done this before in the past, but I'll review it just since we're talking about acids. So here are two chemical structures of acids. We have nitric acid, which is our oxy acid, and this was actually derived from nitrate, one of the 5 big nonmetal 8s that I emphasize in my lecture to know about. And this is acetic acid. This one is derived from acetate. It's a little bit trickier. I don't have the trick with the 4, but again, acetate was an ion that was expected for you guys to be familiar with. If you look at the models here, anything in red is an oxygen, anything in white is a hydrogen, anything that's black is carbon, and nitrogen is blue. The other thing is in these line drawings, they are omitting the lone pairs. So if you really wanted to recall, this would have to have 3 lone pairs, have its octet. This would have 2 lone pairs. This would have 2 lone pairs. That's why it's bent, because it has 4 bonds or 4 electron groups, 2 bonds, 2 lone pairs, giving it a bent molecular geometry. Over here, we would have 2 lone pairs, 2 lone pairs, and don't forget there's actually a bond right there between that oxygen and hydrogen. And the actual hydrogen that's going to be released as a proton that's behaving as an acid is the hydrogen that's attached to the oxygen, and that's due to the difference in electronegativity. But essentially, acids are covalent compounds, molecular compounds that can form an ion, essentially a hydrogen cation, okay? And an anion that's going to dissolve as well. So basically, when the hydrogen dissociates, you're going to be left behind with the negative charge. So binary acids have to typically be written with AQ to show that they've been dissolved. If you don't include that, they're typically considered molecular compounds because we can find them in a gaseous state where they don't behave like an acid. So we definitely, whenever we have a binary acid, want to write out AQ. So here are some examples of the binary acids we talked about. We have hydrochloric acid, hydrobromic, and hydrosulfuric. And because there's the aqueous, we are referring to them as acids. Otherwise, if there wasn't an aqueous, you could say hydrogen chloride, hydrogen bromide, and hydrogen sulfide. So basically with acids, they typically write their formulas out with the hydrogen in front. So we have an example of the hydrochloric acid and the sulfuric acid. So again, I said part of this lecture was a review, just to kind of review nomenclature. So the first type of acid we'll talk about is the easier type, the binary, which is composed of just a hydrogen and a nonmetal. They typically have the prefix of hydro, and then they take the root of the nonmetal, and then they add the ic acid suffix to it. So in this example, we see that we have hydrochloric acid. Again, the root is derived from the nonmetal chlorine. And I should have aqueous here to show that it's an acid. This would be hydrobromic, hydrosulfuric, hydrofluoric, and hydroiodic. So this is, again, just a quick review of binary acids. Binary means two, hydrogen, non-metal. The name is derived from the non-metal's root, and then we add the hydro prefix and the ic acid suffix. The one that's a little more challenging was the oxy acids. So I want to do a review of the oxyanions, because really all the oxyacid is, or oxyanion, is a hydrogen removed from the oxyacid. So to review, we were focusing on the 5 big non-metal 8 ions. So in this example, nitric acid is essentially just nitrate with a hydrogen proton or a hydrogen ion added to it. So we know that nitrate's a -1 charge, so I would need 1 H plus, and that would give me the nitric acid. So the ic acid gives the 8 ion once it dissociates its proton. So again, how could you remember those non-metal 8 ions? There was the trick of the 4. So we could take the periodic table, go to the area where the non-metal central atoms are, like nitrogen, chlorine, bromine, iodine, phosphorus, sulfur. And if it's on the 4, it's going to have 4 oxygen. If it's not, it's going to have 3. So with oxyacids, we take the 8 ion, convert it to the ic. We're going to use the 4. So here are a couple examples. Carbonate. Why is carbonate CO3? It's not on the 4. So it's got 3 oxygen. It's a 2- charge. So as a result, I need to add 2 H pluses to make this a neutral compound, which is carbonic acid. So carbonic acid is an example of a diprotic acid. Chlorate. So chlorate is not on the 4. Chlorine's not on the 4, so it has 3 oxygen. It's got a -1 charge, so I only need to add 1 proton, so it's a monoprotic acid, and the 8 ion gives me the ic acid. So then we have nitrate. It's not on the 4, so it has 3. Phosphate, it's actually on the 4. Phosphorus, and so is sulfate. That's why they have 4. And then they produce the 8, the ic acid, the 8, the ic acid, the 8, the ic acid. So nitrate has a -1 charge, so it only has 1 hydrogen as nitric acid. Phosphate has a -3 charge, so I need 3 hydrogens for phosphoric acid. Sulfate has a -2 charge, so I need 2 hydrogens for sulfuric acid. Notice that phosphoric acid has 3 protons, so it's considered triprotic. Sulfuric acid has 2, so that's an example of a diprotic acid. So again, that's review. This is stuff that we've seen before, and this is just an example of all the different acids we've seen. Now, one thing you may notice is not only did we in the past cover the ic acid, but we also covered the us. So the us was 1 less than the ic. So with nitric acid, we know that nitrous has 1 less oxygen. And we see this all around. So sulfuric acid, sulfurous. So sulfuric has 4 oxygens, so sulfurous has 3. They have the same amount of hydrogens because both of the ions, whether it be sulfite or sulfate, have a 2- charge, and that can be seen right here. We also have, the perchlorate, if you remember, has 1 more oxygen than chlorate. Chlorite has 1 less, and hypochlorite has 2 less. So that results in our perchloric acid, because perchlorate, perchloric. Chloric acid is derived from my chlorate. The chlorus is 1 less, just like I said earlier. And then the hypochlorous is 2 less oxygen. And then I throw in acetic acid because this is one you just have to know. It's really common. It's a weak acid, weak carboxylic acid that we deal with a lot. You've seen it in some of your labs and when we do titrations with vinegar and things like that. So just as a review, let's just practice. Can we select the correct name for each of the following acids? So HBr. Now, again, there should be an aqueous, but all the choices are acids. So which one would it be? Well, it's binary, so it has to have the hydro prefix. So just based on the process of elimination, it's got to be number 3, hydrobromic acid. Now for B, we're going to use the 4. And where is carbon? Carbon is there. So I see that I have 3 oxygen because it's not on the 4, so that must be carbonate, which results in giving me carbonic, because the 8 ion gives me the ic acid. So again, carbonic acid, H2CO3. If I had 2 H pluses and a CO3 2 minus, that's how I get my carbonic acid, and this is my carbonate. So the 8 ion helps me derive the ic acid. This one's a little trickier because I see that the chlorine has 4, but chlorine is not on the 4. So really my chlorate is ClO3. So this is derived from ClO4 minus, which means it has 1 more than chlorate. So this must be perchlorate. So if this is perchlorate, this must be perchloric acid. So let's see how we do here, right? So you can pause this, look at it. But for this first one, first, is it binary? It is. There's 2 elements. So this would be hydrosulfuric. I like to write hydrosulfuric acid out for you over and over. If you look at, my nomenclature when we cover polyatomic ions, I do this. But I like writing the sulfur because I write the full, unlike other binaries where I just kind of write out, or it's just written as a root. You write out the full sulfur and then the ic acid. B, that's acetic acid. That's one you need to know. Now, this is no longer binary. It's an oxyacid. What is it derived from? Well, it's probably derived from this, which is nitrate. So that would make this nitric acid. Now for D, it's derived from this oxy anion, but that's not sulfate. Sulfate is SO4 2 minus. So this is 1 less. So this is sulfite. So this doesn't give me sulfuric acid, but it gives me sulfurous. Now this is not a binary acid, and this is why I bring this one up, but its nomenclature is like a binary. Okay, this is hydrocyanic acid. This is the cyanide ion. Okay, it's a polyatomic ion, cyanide. And it's actually, if you wanted to draw the Lewis dot structure, this would be the Lewis dot structure. And it has an extra electron. That's why there's a negative charge. Where did it get the extra electron? Well, really, you can think of it as for the hydrogen hydrocyanic acid. Here's hydrogen, here's a bond to the carbon. There's 4 bonds. 1 electron comes from this carbon, 1's coming from hydrogen, but it's taken away, giving me the proton, and the extra electron right there is why cyanide has a negative charge. But this is hydrocyanic acid. That's one of the reasons why I wanted to go over this. Is it's not really a binary acid, but it follows those rules of nomenclature for a binary acid. What about chlorous acid? So it's not chloric, it's 1 less, right? So chlorite would be ClO2 minus, so chlorous acid. Phosphoric acid, so that's ic acid, derived from phosphate. So phosphoric acid, and why is it a triprotic? Because phosphate has a 3 negative. Hydrophosphoric, okay, hydro means it must be binary. So it's H3P. Why is it triprotic? Because phosphide is a 3 minus. So if I look at the periodic table, phosphorus is in group 5A. It's 3 away from a noble gas. It forms a 3 negative charge. Carbonic acid, by now you're getting really comfortable with carbonic acid. It's derived from bicarbonate. We've talked about this. We'll talk also about how carbonic acid in our last lecture, we'll talk about how it's part of the buffer system in our blood. And then last but not least, you got hydronitric. Hydro means it is binary. Nitric derived from nitride, YN3 minus, because it's in group 5A. So this must also be triprotic. Okay. So now that we've reviewed naming acids, we are going to go into basically, the different types of definitions of acids. So the most common is the Arrhenius definition of acids and bases. This is kind of the one we've been using all along. And what the Arrhenius is, it basically produces, when you throw the acid in water, it dissociates and gives me a bunch of hydrogen ions, which we also call protons. So HCl is a covalent compound, right? It's molecular. And the reason why it has a molecular bond, it's two nonmetals sharing electrons. And I could even go back to the old school. Here's, one valence electron from hydrogen, because it's in group 1A. Chlorine's group 7A, so it has 7 valence electrons. It wants an octet, so what do? They share these electrons and make a bond. So this is a covalent compound because they're sharing electrons. It's a nonmetal with a nonmetal. There's no ions. But as soon as I put it in water, that's why this is an acid. What does it do? It dissociates as if it's ionic, and it gives me a bunch of H+ ions or protons or hydrogen ions. And what's left behind is the chloride ion. And basically what's happening is, you can think of the 2 electrons are being taken away from the chloride, the hydrogen losing an electron, and the chloride getting the electron from hydrogen and forming a negative charge. But there really isn't just a free-floating hydrogen ion in solution. So, and the reason is hydrogen ions are very reactive, okay? They see water, and they see that water has 2 lone pairs, and they want, because they're positively charged, they want to react with those lone pairs, those negative charges. And what they actually do is they produce what's referred to as the hydronium ion. And if I was to use line formula, right, the hydronium ion would look like this, where there is only now 1 lone pair on the oxygen, and there would be 3 bonds. And overall, this would have a positive charge of +1 because the proton comes in and doesn't bring any additional electrons. So in water, hydrogen ions, pretty much what's going to happen is they're going to attach. There's every ion that dissolves in water, if you remember from solution chemistry chapter 9, gets surrounded by the solvent. Remember, that was solvation. So every solute particle is surrounded by the solvent. Well, if the proton, the hydrogen ion, is surrounded by water, it's going to react with the water to produce this hydronium ion. So even though this is used interchangeably, and it's a lot easier to write this, and it's okay to write just the hydrogen ion, in reality, there is no free-floating hydrogen ion. It's hydronium. So I just want people to be aware of that. So what are some of the base characteristics? Well, bases are bitter. They feel slippery, so you can think of like cleaning supplies. And they turn litmus paper not red, but blue. So I always tell students you can remember it by thinking BB. Bases turn litmus paper blue. Some common: sodium hydroxide, also known as lye, found in like liquid Drano, potassium hydroxide, sodium bicarbonate, ammonia. This is also in Windex. This is baking soda. So they're pretty prevalent. So what is the definition of an Arrhenius base? Well, it produces hydroxide ions. The difference is, typically your Arrhenius bases are ionic compounds. So you have a metal with the hydroxide ion. So when you throw it in water, this ionic compound dissociates and it produces your ions because it's an ionic compound. So in this example, sodium hydroxide gives me the sodium ions and the hydroxide ions. Molecular compounds containing an OH group, like methanol, they don't dissociate because it's not a hydroxide ion. They're not really bases. These are molecular compounds. These are molecules. And so they don't dissociate. What we do see is with metals, because it's ionic, they dissociate and give us ions. So again, the Arrhenius acid, it's a covalent compound, but it does dissociate to give me ions. And now what I want to do is I want to look at a new definition. Okay, so far the definition of an acid, the Arrhenius acid, gives me protons. Arrhenius base gives me hydroxides. We did that with our neutralization reactions in the past. But there is another definition, and it's called the Bronsted-Lowry definition. The Bronsted-Lowry acid is a proton donor, and the base is an acceptor. So here's an example. Now, the reason why I like going over this is what we notice when we look at this reaction is that the hydrogen chloride or the hydrochloric acid, it's the acid because it donates the proton. Well, how do I know that? Here's the hydrogen, here's the chloride. This hydrogen attaches to the water molecule to form that hydronium ion that we mentioned. So there is a transfer of the proton to the water. So because the hydrochloric acid donates a proton, it's the acid. But according to Bronsted-Lowry definition, even though there's no dissociation giving me a hydroxide, like Arrhenius bases or Arrhenius bases, the Bronsted-Lowry base simply has to accept the proton. So in this case, water is behaving as a base because it accepts a proton. And what's left behind, again, once the water accepts a proton, it's a hydronium ion. And once the hydrochloric acid donates the proton, all that's left is the chloride ion. And this is actually considered an acidic solution. Why? Because we measure acidity by the concentration of this hydronium ion. So basically, acids donate protons in water. Water's because it's a solvent and the protons are very reactive, surrounds the hydrogen and they attach to produce hydronium. Hydronium is a measurement of acidity. So that's how we measure acids. So in this case, water is behaving as a base. So with the Bronsted-Lowry definition, you have to look at the whole reaction to see where is the hydrogen going, right? Who's giving up the proton, who's accepting it. That's the only way to identify who's the acid and base. So according to the Bronsted-Lowry definition, these are working together. They're not separate. So let's do an example of a Bronsted-Lowry base, okay? So in the reaction of ammonia and water, we're going to see that the ammonia is the base and water behaves as the acid. So in this particular case, right, we have ammonia. And what you don't see is there's a lone pair. Then we have our water. And what happens is, if we look on this side, the ammonia, how is it different? Well, there's a nitrogen, there's these hydrogens, and then there's that extra hydrogen. Where did it get it from? The water. The water donated a proton. So that makes the water the Bronsted-Lowry acid. The ammonia accepted the base or accepted the proton. So it is the base. So now I produce the ammonium ion and the hydroxide ion. One thing that I want to mention that is different in this example, and I'll go back a little bit, I apologize. If we look earlier when we talked about the Arrhenius with sodium hydroxide, because it was ionic and there's 100% dissociation, the arrow's only going in one direction. Okay. When we talked about the acid, the Bronsted-Lowry acid definition with the hydrochloric acid, we're seeing that it's going in one direction in this case because it's a strong acid. What we notice here is there's a double arrow. The reason why there's a double arrow is this is actually in equilibrium. What that means is there's equal forward and reverse reaction rates. We don't have equal quantities, okay? In fact, this doesn't happen a lot. This doesn't happen very frequently. We'll be measuring that with Ks. But water does behave, in this case, in the presence of ammonia, which can accept the proton. Water behaves as an acid. Why? Because ammonia will accept the proton and behaves as a base. So when there's this exchange of protons, and we have to keep track, according to Bronsted-Lowry definition, of the entire reaction so that we can identify the acid and base. But once we do that, we notice that the acid, so in this case, if I have hydrogen fluoride, right, or hydrofluoric acid, once it donates its proton, so basically I could do this, H plus F minus, it's no longer an acid. So right now it's an acid because it's donating. Once it's done that, it's no longer an acid, it's referred to as the conjugate base. So the acid, once it loses its proton and it no longer has a proton to donate, you can't call it an acid anymore. So what do you call it? The conjugate base. Well, what's the opposite? Well, where did the proton go? Well, let's say I have water. And here's the H plus. And it accepts, the water accepts a proton that the hydrofluoric acid gave. And now I see that it produces the hydronium ion. So what did water do? Well, water accepted the proton. So that makes water what? The base. But now that it has this extra H plus, it's no longer a base anymore. So what do we call it? Well, the base became what? The conjugate acid. So the acid becomes a conjugate base. The base becomes a conjugate acid. They basically become the opposite. So a base, H2O, accepts the proton to form the conjugate acid. There are two conjugate acid base pairs. So one, hydrogen fluoride or hydrofluoric acid, and the conjugate base fluoride. The other conjugate acid base pair is water, which is a base, and the hydronium ion, which is a conjugate acid. Now, why do we need to be able to recognize when we have Bronsted-Lowry acid-base reactions, what's the conjugate acid and base? Because it helps us identify where the proton's going. So the only difference is we're moving an H plus. So the acid is losing the H plus and the base is gaining an H plus. So here's an example, right? And I have to look at the whole equation. I have to look at both sides, right? So here I have bicarbonate and water. Over here I have carbonic acid and hydroxide. So what could have possibly happened? The water moved a proton. So when you take HCO3 minus, which is bicarbonate, and H plus, what do you get? Carbonic acid. So the bicarbonate is the base. Why? What did it do? It accepts the H plus. It's a proton acceptor. So once it accepts the proton, it produces what? The conjugate acid. Now what's water? Well, water's the acid. Why? It donates the H plus. So what do you do? When H2O donates an H plus, what's left? An OH minus. We've been seeing this all along with neutralization reactions. Pretty much almost every net ionic reaction for an acid-base neutralization is just the reverse of this. So now if I take away a proton from water, all's left is hydroxide, and that's what this is. So my acid becomes my conjugate base. What are my acid-base pairs? My acid-base pairs would be the bicarbonate ion with carbonic acid. So the base becomes a conjugate acid, and water, the acid, becomes the conjugate base. By the way, this is a buffer in our blood. So why am I going over that? Well, now you have to think to yourself, well, what's going to be the conjugate base of the following? So in A, the conjugate base, you can think of it as once the acid does its work, which is donate a proton, whatever's left over is the conjugate base. So you literally can think of, if I donated a proton, what would be left? Bromide, right? What about here? Well, if I only donated one, it'd be the hydrogen sulfide. If I donate two, then I would go all the way to the sulfide. Same thing here. If I donate one, H plus, bicarbonate. If I keep going, then it'd be, and we'll talk about this, but for the most part, we're going to just stop after one for the diprotics. Right? So what would be my conjugate bases? If I eliminate the H pluses, my bromide, hydrogen sulfide, bicarbonate or hydrogen carbonate. So what would the conjugate acids for these following bases be? Well, add an H plus. Well, if I combine these two, I'd get nitrous acid. What if I add an H plus here? Ammonium. I have to keep the positive charge because this was neutral and there's a positive, so that has to be positive. The reason why this is neutral is this is negative, this is positive, so that becomes neutral. So you can think of it as -1 + 1 = 0. If you go to ammonia, number 2, 0 + 1 would equal +1. That's why ammonium's +1. If I add a proton to the hydroxide, what is that? Remember, HOH, water. So remember, we would always balance it that way. And why is it neutral? -1 + 1 = 0. So there you go. There are your examples of each. So we want to make sure if we see reactions, can we identify the acid and the base, and then the conjugate acid and the conjugate base? So if we look at C in exercise 3, where is the proton going? So you have to look at both sides, right? And what stands out to me is the hydronium. Whenever I see that, that means water had to do what? Water had to accept a proton. So if water had to accept a proton, water is a base because it accepts it. Well, if water is accepting, then the sulfuric acid is donating, and it's the acid. Okay. The H2O became, and I know this is switched, I apologize for that, I just noticed, but the H2O becomes the hydronium, so now the base becomes a conjugate acid. And the acid becomes a conjugate base because it lost one of the protons. Let's try D. So what? If I look, I see that the bicarbonate's negative, and over here I have carbonic acid. What does that mean? This must have gained what? An H plus. Well, where did he get it from? The water. So if water loses an H plus, what's left? OH minus. So you have to look at the transfer. So the bicarbonate, because it accepts, it's the Bronsted-Lowry base. The water donates, it's the acid. Once the base accepts the proton, right, it becomes the conjugate acid. And once the acid donates the proton, it becomes the conjugate base. And then you could write out your conjugate acid base pairs. And what we notice is in this case, and I know there's a lot of writing on here, so I apologize, but let me kind of erase this for you, make it a little bit clearer. If we notice in part C, the water is behaving like a base. Why? It's in the presence of what? An acid. In D, water is behaving as an acid. Why? It's in the presence of the base. So water is very unique. If it's in the presence of an acid that donates a proton, it'll accept it and behave as a base. If it's in the presence of a base, it will neutralize that base and donate a proton and behave like an acid. So it has the capability of doing both. So that makes it what's referred to as amphoteric. If it's in the presence of an acid, it'll behave as a base to neutralize it. If it's in the presence of a base, it'll behave like an acid to help neutralize it. So since we're talking about acids and definitions, and how do we know if an acid is strong or weak? So this also goes back to our discussion of solution chem when we talked about weak and strong electrolytes. And basically, one of the topics was strong acids completely ionized. So even though they're covalent compounds, they break apart 100% in water. So that's why hydrochloric acid, which is one of the 6 strong acids, completely dissociates. And that's why we only see the arrow going in one direction. So hydrochloric acid is a strong acid because it completely breaks up into ions. And as a result, not only is hydrochloric acid a strong acid, it's a strong electrolyte. So when I throw it in water, only ions will be present. There are 6 strong acids, and I've spoken about this, but 3 of them are binary: the hydroiodic, hydrochloric, and hydrobromic. The other 3 are your oxyanions. This is also why I reviewed the nomenclature for acids, okay? So we have the perchloric, the sulfuric, and the nitric. 5 of the acids of the strong acids are all monoprotic. So that means there's only 1 proton that ionizes. Sulfuric acid is an example of a diprotic. Again, why? It has 2 protons. Typically, it ionizes 100% as 1 proton, and then the hydrogen sulfate or the bisulfate. The bisulfate can behave as an acid. It can dissociate a proton, but it's a weak acid, so it doesn't completely ionize. So it's not one of the 6 strong. So we can't say it goes all the way to SO4 2- and H+. So basically, an ionizable proton is one that becomes an H+ ion in solution. So how are weak acids different? They only ionize a small percentage. And I like to tell people it is far less than 1. So less than 1%, way less. So a weak acid, it only breaks down part of the time. So what do we show? Well, because there's partial ionization, we show the double arrow. And the double arrow means equilibrium, dynamic equilibrium. So I have the hydrogen fluoric acid and water. as a reactant moving in the forward direction. And then I have the hydronium and the fluoride moving in the reverse. The rates of the reactions are equal. That's a dynamic equilibrium, but it doesn't mean I have the same concentrations. So with weak acids, my K of equilibrium would be less than 1. Why? Because the reactants are favored. That's what we talked about in chapter 10 with our equilibrium constants. Okay? So what does that look like? When I throw hydrogen fluoride or hydrofluoric acid in water, I only get a few ions. The majority of it remains as a covalent compound. So because there's only partial dissociation, I show the double arrow. It's considered dynamic equilibrium because these two can collide to produce the hydrogen fluoride, and then the hydrogen fluoride could collide with the water to produce these two ions. So the reverse and forward are going in equal rates, but not equal amounts. It's also considered dynamic equilibrium because it's a closed system, because it's dissolved in the water, right? The condensed liquid-based solution. So essentially, the stronger the acid, the weaker the conjugate base. So because what will happen is once the acid does its job, it'll have a conjugate base. So this is my acid. How do I know it's an acid? It's donating a proton to water, so water would be my base. So the acid becomes the conjugate base. Okay? If the acid is really strong, then my base is going to be weak because it's not going to want to go in the reverse direction. So how do you look at it? The stronger acid, let's say the hydroiodic acid is the strongest of those 6 strong. The iodide ion is the weakest base, the weakest conjugate base. So the weakest, these are still all strong, complete dissociation, but we're just saying relative. The nitric acid, which is still a strong acid, but the weakest of the 6, has the strongest conjugate base, nitrate. So weaker acids have a varying degree of strength. The stronger the acid, the weaker the conjugate base. But really, if we want to look at weak acids, we shouldn't be looking at the strong acids. We should be looking at weak acids, right? So what's an example of a weak acid? Hydrofluoric acid. What's another example? Well, according to Bronsted-Lowry definition, if water's in the presence of a base, it could behave as a proton donor and neutralize it, and as a weak acid. So we see water as a very weak acid. It's neutral. So as a result, its conjugate base, hydroxide, because the difference is, how do I go from an acid to a base? I got to donate that proton. And if I lose a proton from water, all that's left is hydroxide. So the hydroxide is an extremely strong base because it's a conjugate base to a really weak acid, water. The stronger the acid, so the hydronium ion is stronger than all these weak acids. It has the weakest conjugate base, water. And that makes sense because water, again, is neutral. Yeah. So going back to determining the strong acids and weak acids, in the past, I said it's a lot easier to know the 6 strong acids than memorizing all of the weak bases. And that's true because the majority, or all the weak acids, sorry, I said bases, but it's the same concept. The majority of your acids are weak acids. So we're just going to know the 6 strong acids, and the majority of them are weak. The majority of acids are weak, which means that their conjugate bases are relatively strong. So here is still kind of that discussion. I have carbonic acid as a diprotic acid. It partially dissociates in water, giving up 1 hydrogen at a time. So the double arrow is showing that's weak. And I'm donating my proton, behaving like an acid, and then water is behaving as a base. And then water, once it accepts the proton, becomes a hydronium ion and is a conjugate acid. And then my carbonic acid becomes a conjugate base, the bicarbonate ion or hydrogen carbonate. But the hydrogen carbonate is also a weak acid, and it could, in theory, have a second dissociation and produce another hydronium ion. So the bicarbonate in a smaller amount, and that's why we have a double arrow, could donate a proton and go all the way to carbonate. If it does that, the carbonate is the conjugate base, right, to the bicarbonate, which in this reaction is an acid. But the carbonate is the conjugate base to the conjugate base bicarbonate to carbonic acid. So believe it or not, carbonate's a pretty strong base. Why? Because it's coming from such a weak acid. Same concept here, the H2SO4. It's diprotic, but only one of the protons dissociates completely. So in sulfuric acid, it's a strong acid, it's 100% dissociation, but only one proton. So I produce hydronium and then the bisulfate or the hydrogen sulfate. And this is an extremely weak conjugate base. Why? Because this is such a strong acid. So this is a very weak conjugate base. Where in the reverse, this is a very strong conjugate base because this is a very weak acid. This is a weak conjugate base because it's a strong acid. But again, I have this bisulfate that has a hydrogen that could donate it to water to produce the sulfate. So this is a very weak conjugate base because it's the conjugate base to a weak conjugate base. So with bases, it's based on, the strength is based on the dissociation. So sodium hydroxide, right? We know that sodium is always soluble. So it completely ionizes. So again, we have 6 strong bases, group 1A and group 2A. We've talked about it. Group 1A, because they're always soluble. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide. Now, strontium hydroxide, calcium hydroxide, and barium hydroxide have low solubility, but they dissociate completely. So those are considered strong bases. So the arrow is just showing complete dissociation, giving me a large concentration of hydroxide ions, meaning a strong base and also a strong electrolyte. So strong acids and bases are essentially electrolytes, and they dissociate completely, giving me a strong electrolyte. Weak bases are like weak acids. They only partially ionize. That's why we see a double arrow. And typically, the Bronsted-Lowry bases, which were the proton acceptors that we talked about, what happens is they are dissolved in water, and water only sometimes will donate a proton and behave as an acid. And because this accepts the proton, is my base, and it's the Bronsted-Lowry base, what I end up getting is I get a small quantity of hydroxides from the water. So that's the advantage of the Bronsted-Lowry definition, is recognizing I could have this weak base that doesn't break apart and give me, these hydroxide ions. Instead, water neutralizes it some of the time. That's why it's a double arrow. and produces a small amount of hydroxides. And that's why it's considered a weak base, because the more hydroxide we have, the stronger the base. Well, if I only have a little bit of hydroxide from the water behaving as an acid, well, then I'm going to be a weaker base. So in that example with ammonia, we added ammonia. It reacts sometimes with water to produce ammonium and hydroxide. And I have a small concentration of hydroxide now, which means I'm a weak base. And most of what I have is the molecule of ammonia in water. And I don't have a lot of hydroxides. That's why it's an example of a weak base. But really a nice way to measure strength rather than think of it qualitatively, because qualitatively we could just say there's 6 strong acids, all the rest are weak. There's 6 strong bases, all the rest are weak. We could actually use an acid dissociation constant, which we refer to as Ka, the A for acid dissociation, the K from what we saw in chapter 10 are equilibrium constants. So whenever we have an acid thrown in water, it donates the proton to produces hydronium and the conjugate base. So now what can we do? Well, we can set up an equilibrium expression. Equilibrium is products over reactants. Okay. Remember, we're only using for Ks, your equilibrium constants, gases and aqueous. All right. So when I look at my products, I have the hydronium ion and the conjugate base to the weak acid. So I have my hydronium and the conjugate base. On the reactant side, notice I do not include water in the equilibrium expression. Why? The concentration doesn't change. The solvent is so abundant, if one of them accepts a proton, it's still mostly just water anyways. So we don't incorporate this in the expression because, again, liquids and solids in heterogeneous equilibria are not included. But we do include the weak acid because it's dissolved in water into the equilibrium acid dissociation constant. So can we do this for a real acid? Well, let's take formic acid. So formic acid is HCHO2. Okay. So you could think of formic acid as, you know, there you go. There's your formic acid. It's a carboxylic acid, and the proton that's being dissociated is out right there. So in this balance equation, we don't necessarily see that, but what I want you to think of is I have a proton, and I see that because this is in front, going to the water, producing hydronium and the formaldehyde. So the formate, the formate. So if I look at this, this is donating the proton. This is accepting. So water is my Bronsted-Lowry base. And this is my weak acid, the formic acid. And then the formate is my conjugate base. And the hydronium, once the water accepts the proton, the base becomes my conjugate acid. So now, can I write a Ka? By the way, this is what we see in, you know, bee stings and ant stings. It's if you ever got stung and it itches and it swells up, it's the formic acid. It's a weak acid. But the equilibrium expression is what? Products over reactants. So my products, the hydronium ion and the formate, hydronium ion and formate, they're included because they're both aqueous. And then reactants, I include the formic acid because it's aqueous, but I do not include water. But really, the reason why I want to go over this is this equilibrium expression for the acid dissociation, which is products over reactants. If you look at this quotient, what do I notice? It's very small. This number is far less than 1. So what does that mean? I don't have a lot of products produced. Right, this quotient is very small. Why? Because the numerator is larger. There's more water, well, water's not included. There's more formic acid than there is formate and hydronium ion. Why? It only partially dissociates. So I know this is a weak acid because there's not a lot of hydronium produced in this expression. That's what Ka tells me, products over reactants. So the Ka ties into our equilibrium constants from chapter 10, but it helps us now, instead of just saying, oh, this is a weak acid, you know, because it's not one of the 6 strong, instead of just qualitatively understanding weak acids, now we can quantitatively use the Ka to kind of compare it quantitatively. So when I look at all these weak acids, I could look at their Ka values and see which ones would be weaker, right? So we got phosphoric acid. It's a weak acid. Why? Ka is less than 1. So that means it's only going to dissociate into hydronium a little bit, right? Way less than 1. Well, it makes sense then that its conjugate base, right? Because how do I go from here to here? I donate a proton, right? I just lose a proton. So this is the conjugate base to phosphoric acid, which is a weak acid. Well, of course, the conjugate base to this weak acid is going to be even a weaker acid. And guess what this is? This is another donation because this was triprotic. So I donate a second time. Now I have that hydrogen phosphate, and now it's even weaker of an acid. So this allows us to see, okay, well, this is by far a much weaker acid than that, based on the magnitude of Ka. So what we can also do is write out Ka expressions, plug in concentrations, and solve for Ka like we did in chapter 10. So how do we do this? Well, the first thing you want to do is you have to write out the balance equation. So we throw this weak acid in water. How do I know this is a weak acid? It's not one of the 6 strong. It's not hydrochloric, hydrobromic, hydroiodic, perchloric, nitric, or sulfuric. So I'm going to write double arrows. I'm going to donate. By the way, this is hypochlorous acid. It's going to donate, gives me the hydronium ion and hypochlorite as the conjugate base. So to get the K equilibrium, it's products over reactants. And I get the hydronium and the hypochlorite, and then the hypochlorous acid on the bottom, and I don't include the water. Why? Because it's a liquid. Its concentration doesn't change. So I can do the same with nitrous acid, plus water. It's double arrow because nitrous is a weak acid, but it can sometimes donate a proton, producing hydronium and the conjugate base nitrite. So what do I do now? Products over reactants. And I leave out the water because it's liquid. So if I was actually given the concentrations of each of these, I could actually solve for that Ka value. Or if given the Ka and two of the concentrations, right, then I could solve for one. So this ties into that earlier chapter. And really what it's doing is prepping us for our next lecture in acid and base chemistry, where we're going to actually be doing pH calculations. And for pH calculations, we have to write a water equilibrium expression or constant. And we'll get into that discussion next time. So I hope you enjoy the review of nomenclature, the new definitions for Arrhenius and Bronsted-Lowry acids and bases and conjugate base pairs, and setting up K of equilibrium for acid dissociation for our weak acids. So thanks so much for watching. I appreciate it.